Alright, so we're going to go through the different shifts of these graphs. A lot of this will go fairly fast, I think, because you understand the concept of the shifts. But we know what an exponential function looks like when a is positive. The first thing we want to do is figure out what happens when a is negative. So we're going to use every part of your y equals editor today. Okay? So when you're in your graphing calculator and you're doing y equals, we're going to use each piece of that. So the first part is put y equal, or y sub 1 is 3 times 2 to the power of x. You guys can't see that. And then y sub 2 is negative 3 times 2 to the power of x. Okay? What I want to know is what happens when you graph those. How does making a negative change your graph? Go ahead and graph it. Tell your neighbor what you see there. Verify that using the table feature of your calculator. Okay, so most of you have done it. What happens? Parker.
It's mirrored over the x-axis.
Good, it's mirrored over the x-axis. So it's a reflection. When a is negative, our graph reflects. It's the corresponding graph, the corresponding positive value over the x-axis. So this y sub 2 is a reflection of y sub 1. So when you see that on your graphing calculator, you go ahead and get mine here. All right. Yeah, geometry's doing some amazing, cool stuff there. Okay, we see it on our graphing calculator. There it is. So y equals 3 times 2 to the power of x. Y equals negative 3 times 2 to the power of x. It looks like a reflection. We verify that using our y equals menu. When x is negative 3, y sub 1 is 0.375, and y sub 2 is negative 3, or 0.375. So the positive value correspond to the negative values there. Okay? A flips it across the y-axis if it becomes negative. All right. So we've got A down. We know B and we know X. Okay? The next thing we want to do is see what happens when we go ahead and change or put a number or an accelerator in front of our x. We're going to call that our constant term. Okay? So if we think of our equation, we have y equals AB. I'm now putting in a k right here. Okay, a small k. The book calls it a small k. I would probably reference that more as a c because we're going to use k in another way. The only reason I put k on the sheet is because the book uses k. I like to reference it more as a C. So I'm going to change all these to C's. And I would have done that ahead of time, but like I said, our textbook calls it a K. All right, just so that we kind of keep it constant there. All right, so we've got y sub 3 is y equals 2x, y sub 4 is 2 times x, and y sub 5 is y equals 1/2 times x. Make sure you turn off y sub 1 and 2 when you do this. So you only see 3, 4, and 5 on there. All right. Once you figure it out, go ahead and tell your neighbor what you think is happening, what it appears to happen. Talk about it there. What's happening? Yes, yeah.
The smaller the number, the wider the graph, and the bigger the number, the narrower the graph.
Okay. Everyone agree? Okay, the first one is it's going to graph y sub 3, y sub 4, and then y sub 5. So when I graph, the first one we see is y sub 3, y equals 2 to the power of x. Second one is 2 times 2 to the power of x. See that one coming up. And then 2 times, or 2 to the 1/2 power of x. Okay. Right, so as this number is getting smaller or closer to 0, as our c is getting smaller or closer to 0, our graph's getting wider. Or the other route to think of it is anytime you have a number attached to your x value, it is like an accelerator. It's like a gas pedal. The faster or the bigger the number is, the faster it's going to infinity. The smaller it is, the slower it's going to infinity. So this is like your accelerator. And we're going to see this when we saw it when we study quadratics. We're going to see it as we study other things this year. But this shows how quickly or how slowly you're moving upward. And that's anytime it's attached to your x there. So if you recall back in what we did earlier in the year, we had y equals a times x minus h, quantity squared plus k. This was our accelerator. That's how quickly our parabola moved upward. Kind of the same idea here. This is our accelerator. Okay, it's attached to that x. All right? Tyler?
What's the letter of the variable that's scratched out?
K.
You changed it.
Our textbook shows that as K, and I'm using C because I'm going to use K later. Okay? So, I'm trying to relate it to what we've done before. Any questions there? Next piece. What do you think would happen if K is negative? Or not K, remember we've changed this to C. What happens if I change that C to a negative? Go ahead and make a prediction and then graph. Do not graph and then make the prediction. Then it's not a prediction any longer. Okay, whose prediction was correct? A couple of you? All right. How many of you predicted it goes across the y-axis? Good. All right. So when we check it, okay, we can check it looking at our table. Notice when x is negative 3, y sub 3 is 0.25, and y sub 6 is 8. Okay? When x is 3, y sub 3 is 8, and y sub 6 is 0.125. So it's a reflection across the y-axis. We make that a negative a term, or negative, a c term there. All right. Next piece. Okay. Let's go ahead and look at what happens if we add or subtract a value to our x. Now, you guys are pretty smart. What is that? What value is that?
Okay.
When we add or subtract to our x, what have we called that all year? Uh-oh. All right, well, go ahead and put it in there. Let's see what we got. That's not good. Okay, what shift was this? Everyone's eyes and ears right here. What shift is it? Yeah.
It like slides, right?
It slides? Yeah, it slides to the left and right, which you guys are calling H. Okay? It slides. Okay, so our original y equals 2 to the power of x. Our second one, y equals 2 to the power x minus 3. And y equals 2 to the power x plus 3. Okay? Now, if we wanted to see if this is actually, how much is it sliding? How far? 3 units, right? This is our h value. Okay? We call this our h value just like when we studied quadratics earlier in the year. I keep coming back to that. When something is coupled with your x. You guys, if you can get this down, it helps you out because it's a common thread across a lot of your patterns. When something's coupled with your x, that value out here that you're adding or subtracting is generally your h value. Okay? It's whatever makes that 0 in there, right? Our a is like our accelerator in our quadratic. Okay, here it was our c if we're putting something outside that. So if I changed this problem up and I said that's 2 to the 4 x minus 3, that would just mean that would shift 3 units over and go up much faster. Because I'm now accelerating it four times. Yeah?
So you said the value that we're subtracting or adding is the h value?
That's your h value, yeah.
Okay, so
Remember, h is whatever makes this 0. Or it's the opposite of what you see there. So
that would be negative.
you'd shift that to negative 3. That one shift to positive 3. So if you think of this, what's our y-intercept on y sub 3? It's not 2. What's our a term here? Right, there's a 1 out there in front of it. Right, that's our a term. So our y-intercept is 1. Our y-intercept here, then, if it's shifting 3 units to the right, should be what?
It's not going to work.
Let's see here. If I go to my table and I find the y-intercept. Y-intercept of my first graph, y sub 3, is when x is 0. It's 1. Okay? In my second graph, my y-intercept is 0.125. Okay? It should be 3 units.
Can I see here for just
Sure.
less than a minute?
Yep. Okay? If we're verifying this, we are looking to see what values for y sub 7 and 8 make 1. So if I look at y sub 7, the value that makes 1 is 3. 3 units away from the value that made 1 there. Okay? For y sub 8, it's 1 here. Right? It shifts at 3 units on the x-axis. So as x is moving, it moves from 0 to negative 3. And from here, it moves from 0 to positive 3. So 1 goes from 0 to positive 3. Or on the other one, 1 goes from 0 to negative 3. Okay? All right, we've got one more shift. What's that shift going to be?
Okay.
The K shift. Tell your neighbor where the K shift's going to be.
Y-axis.
All right, there's our K shift. How many of you were right? K shift goes outside of being coupled with the X. So on a K shift, what should happen with this graph? This one should go up how far?
4.
And this one should go down 4. Okay, so go ahead and verify that real quick. Put them into your calculator, check them out. All right, so we got y equals 2 to the power of x. Y equals 2 to the power of x, all plus 4. And y equals 2 to the power of x, all minus 4. If you checked it, you would see that your y-intercept on the first one is 1. On the second one, it's 4 units higher, or 5. And on the third one, it should be 4 units lower, or negative 3. That's your K shift. So let's summarize real quick our equation now. So we started the day with y equals ab to the x. We now have ab to the c x minus h all plus k. You should know what each of these do. You should know what happens if this is negative. You should know what happens if this one's negative. You should know what happens if this is a big number, farther from 0. You should know what happens if it's close to 0. Or what happens as it moves away from 0. You may summarize like the closer you get to 0, the wider the graph is. All right, that's kind of small there. You should know what h does, what type of shift h makes, and what type of shift k makes. Okay, shifting this way, shifting this way. Negative flips it across. This negative flips it across where? The y-axis. Negative here flips across x-axis. Okay. Far from 0 goes up faster. Closer to 0 goes up slower. All right. Okay. Your assignment today is going to be 1 through 20 on the example side of your sheet. Okay? And we're going to go through a few of those problems together. And then I'm going to change some of the instructions on there because I don't want you to be graphing everything that it says to graph on there. Okay, so once we get this down, am I able to move past this? You guys still need it? Okay. Let's go ahead and take a look at the sheet then.
You said 1 through 20 on the example side, right?
Example side 1 through 20. Don't cross anything out though. We're using the sheet on Monday as well. Okay? All right. So 1 through 20 on the example side. First, we need to change these instructions up. Okay? So if you look at 5 through 16, it says graph. You could check it on your graphing calculator if you want, but I want you to describe how the graph, oops, I'm sorry, I couldn't read that. Describe how the graph will differ from the graph of y equals 2 to the power of x. So describe how this graph will differ, the equation they're giving you, from the graph y equals 2 to the power of x. So everyone looking at 5, verbally tell your neighbor, how's this one going to be different than that one?
Wires at that
Yeah.
How do you find the y intercept when you have an h?
When you have an h,
Yeah.
it's when x is still when x is 0. You plug in 0 for x, that's still your y-intercept. It's just not going to be your a term anymore. That's a good question. Let me come through back to that. Okay, let's number 5. What changes? Yeah. It's not narrower per se. Yeah.
It rises more rapidly.
Okay, and that's kind of I think what Hannah's saying. Okay, based upon what we've studied, what's going on with our graph here? Yeah. All right, let's go ahead and take a look at this. Hold on. Everyone go ahead and grab your calculator. I want you to put, make sure you've turned off all your other plots or deleted them, however you're going to do it. Okay? So go ahead and put in y equals 2 to the power of x, and then y equals 3 to the power of x. And we're going to hit graph. Okay. So on both of these we have Hannah saying that it's going, what did you say, it's getting narrower?
Well,
Okay. Now I want to, okay, what you're saying is getting narrower, and what did you say again?
it increases more rapidly.
It increases more rapidly. And what did you say? It goes to infinity quicker. Okay. Increasing more rapidly, or the base is making it go up faster. Any of those would work, yeah. Going to infinity quicker is fine. Okay. Making sure that you know that this is going up a little faster. Probably don't want to use the term narrower because that mathematically doesn't mean anything right here. Okay. I know what you mean though. Okay. It's approaching infinity quicker. All right. That's all you have to put. That's it. You don't have to graph it or anything. If you want to check afterwards, you can. Lee had a good question. She said, hey, what happens if you have an h term? How do you find your y-intercept? So for instance, on 12, your y-intercept is still always when it's not a here. So think back to default. Y-intercept is when what equals what? Y-intercept.
Oh, the wire.
Yeah.
A when h and k are 0.
When h and k are 0, but they're not. So what'd you say?
So when x is 0.
Good. Y-intercept is always when x is 0. Always. Always. Doesn't matter what else anything looks like. Your y-intercept always has to be when x is 0, right? Just by definition. For those of you who aren't following along, There's my y-axis. Doesn't matter where I hit it. That coordinate always starts with 0, comma. Always. So even if you have the most messed up looking polynomial, you have x to the millionth plus 3x to the 900,000th, it doesn't matter. By the time you're done, it still comes down to your y-intercept is when x is 0. Because your coordinate is 0 something. Okay? So when you get to this messy stuff, Lee's question was a great one. When we get here, we can't go, well, the y-intercept's 2. It's not anymore. Because when I put 0 in here, that just gives me a power of 2, which makes that 4 times 2 is 8. The y-intercept here is 8. Okay? So if you didn't know that answer to that question, make sure you write it down, that the y-intercept is when x is 0. All right. Any questions what to do there? Yeah.
Do you have to write all the differences or just one difference because they have multiple differences?
Yeah, I want you to try to get as many differences as you can there. It's gonna take that graph, it's gonna become narrower, it's gonna flip it, it's gonna shift it this way or that way. Okay? All right. Let's go ahead and take a look at number 17. And talk about half-life here. I wrote all over my paper, but that's okay. Number 17. Number 17, 50 milligrams of I-123, which was used in thyroid scans, has a half-life of 13 hours. So half-life is the time it takes half of a material to decay or decompose. So just based upon the term half-life and what it means, is this a growth or a decay function?
Decay.
It's just decay. So if we're writing an exponential decay function for this, well, we have it in y equals ab to the x. And we could have the h and the k in there, but we're not going to have it in this. Okay? What do we start with? Yeah.
B be 0.5 because that's
Okay, so you jump to b, yeah. b is 1/2. Why? Because that's our decay, or 0.5. Anytime you're dealing with half-life, you're decaying a b equaling 1/2. What is our initial, yeah, Todd?
Isn't it 50 milligrams?
Yeah, our initial value is 50 milligrams. That's our A. Remember, that's your starting amount. What is I-123? Where do we put that number? Good, that's the name, man. All right? We don't put that number anywhere. It's the name of it. Okay? Now it goes, so our equation is that. Says, has a half-life of 13 hours. What's after 48 hours? Well, they're asking us how much will be left after 48 hours. So how many half-lives are going to occur in 48 hours?
3.7.
Is around 3, a little more than 3, right? How do you figure that out? Yeah, you divide 48 by 3. So you have to think logically. You have to go, okay, after 13 hours, or it has a half-life of 13 hours after 48 hours. Well, that means I need to take the 48 and figure out how many 13s there are.
3.692.
Cool. And so rather than having to possibly round it, I'm just going to make this my power up here. So the amount I should have left better be, should it be greater or less than 50?
Less.
Should be less. All right. What is it?
3.87.
3.87.
Seven.
All right. Unbelievable. That's milligrams. Will you ever have none left? No. You never can get to 0 if you keep cutting in half, right? Okay. Any questions? All right. Go for it, man. That is your cool guy assignment. All right, so how's it going? Good?
Yes.
Everyone done with 1?
No, not with one. Oh, which is
Everyone get the equation for 1?
I'm on 18.
18, nice. Man. Everyone might want to look at 1.
What does the base mean?
What is the base?
Yeah.
The base is your B. Yeah. So that's nice of them to give us the base. What are we missing? A. How do we find A? Lily? Yeah, plug this x and y in. So if we plug in x and y, we can find A. A is 1 over 9. If A is 1 over 9, is that our equation? No, that just tells us A. We know in order to write an equation in exponential form, you need to know A and B. A is 1/9. B is 3. We can now write y equals 1/9 times 3 to the x. And that's what we're graphing. That's why you have graph paper. The only graphs you have on this assignment are 1 through 4. Okay? Make sure you use an approach. You're going to have to change. On my graph paper I gave you, you're probably going to have to change the scale. I have it going from -10 to 10. Go ahead and just cross out the -10 and 10 if you need to. Okay? All right. Assignments 1 through 20.